Define gravitational field strength. So again, they're saying define, which means that we will usually talk in terms of the mathematical expression. We know that gravitational field strength is defined as the gravitational force exerted on a unit mass. So it's the gravitational force that is acting per unit mass. Force acting per unit mass. Next, we have an isolated planet, is a uniform sphere of radius. So the radius is specified. Its mass of this many kilograms is also specified, may be considered to be a point mass and concentrated at its center. The planet rotates about its axis with a period of 24.6 hours. So this is my planet, and this is some axis about which it is performing some rotation, and the time that it takes to complete one rotation is 24.6 hours. For an object resting on the surface of the planet at the equator, suppose that this is the equator, and there is an object sitting on this equator, and it's resting, as in its velocity is 0 itself, and we are to calculate the gravitational field strength up to 3 significant figures, right? So we know that gravitational field strength, G, is given as the product of Gm over r squared. Now we have G is the gravitational constant, which is 6.67 into 10 raised to power minus 11. The mass of the planet is given as 6.42 into 10 raised to power 23 kilograms. And then you divide it by the square of the radius of the planet, which is the distance from the center to the surface. And it turns out to be 3.39 into 10 raised to power 6 meters, which is, if you do the math, this gives you about 3.73 newtons per kilogram, which means that the field strength for this planet is 3.73 newtons per kilogram. Next, we are required to compute the centripetal acceleration. Now, we know centripetal acceleration is AC is equal to r times omega squared. Now, omega is what? It is one complete revolution, 2 pi, divided by the time that it takes to complete that revolution. Now, the time that it takes to complete that revolution is specified to us. It's given as 24.6 hours. But in 1 hour, there are how many seconds? 3,600 seconds. So we convert it into seconds. Now, we'll use this in this equation, AC. R is again specified. It is the radius of the planet. So 3.39 into 10 raised to power 6 times the square of this thing, 2 pi over 24.6 into 3600 squared. And this turns out to be 0.0171 meters per second squared. Next, we are required to calculate the force per unit mass exerted on the object by the surface of the planet. So again, if actually I'll bring the figure down from here. So we have, this is what a picture looks like, and if I put it over here, we can see that for this object there is some gravity that is acting to the center, and then there is an opposite, equal but opposite force on this other side, right? Now we know that the sum or resultant force from Newton's second law is F is equal to ma, where a is just any acceleration, not centripetal, not gravitational. It is just any generalized acceleration. Now we want to compute the net acceleration on this system. The net acceleration should be the difference between the acceleration due to gravity of the planet 3.73 minus the centripetal acceleration, which is 0.0171. This would be your net acceleration, and force per unit mass would be F over m is equal to the net acceleration, which is, if you compute this thing, you get 3.71 newtons per kilogram.